welcome, and we were discussing in fact about the equivalent circuit and torque slip characteristics of a single phase induction motor running on single winding. Okay. And then the torque slip characteristics must pass through at s equal to 1 it is 0. Unlike 3 phase induction motor, there was a definite starting torque, but in case of single phase induction motor, starting torque will not be there. And then at any slip, of course, if it operates, there will be torque developed, and the equivalent circuit from this the net torque at any slip can be calculated as R 1 x 1, and then that parallel branch equivalent impedance I denote it by x f here, and then the backward field R b and x b. This R f x f is nothing but this one, R 2 dashed by 2 s at any slip, and this is x 2 dashed, and this is x m by 2. This is R f x f is this one. Similarly, R b x b is R 2 dashed by 2 into 2 minus s, and this is x 2 dashed, and this is x m by 2. This is also x m by 2. So this can be brought in this one. Now, what I am telling, the current in this magnetizing inductance decides the strength of the field. So current in this magnetizing branch will be decided by the voltage coming here. Let this voltage be E f and this voltage be E b. Then E b by E f by x m by 2 will be the magnetizing current here, that will decide the strength of the forward motor field. Similarly, E b, this voltage, that is E b by x m by 2 will decide the magnetizing current here, and as you can see, the value of E f and E b will be same when s equal to 1, but when it is not, then these voltages will be different. For forward motoring mode, that is if E f is greater than E b, then the strength of the forward field will be more and strength of the backward field will be less. And both of them, of course, will run at synchronous speed in the opposite direction. That is what I was trying to convey. Now, let us see what happens at any slip at s not equal to 1. This is the situation. So, at any slip s for forward motor slip, S f I am not writing, it is understood it is forward motor slip I am talking about. So, if this is the case, then the strength of forward field, if it is like this, M b will be strength of the backward field will be less, this length will be less, and it is moving in the forward direction. Suppose the forward direction is this way, omega, this is the backward direction. So, motor will run along the direction of the forward field, and the field which moves along the same direction as that of the rotor rotation, I have called that to be your forward field. In any case, so two lengths M f and M b are moving in the opposite direction. So, what will be the locus of that resultant field? It is interesting to examine that. So, at some times they will be, as they are moving, they will be together like this, MF, MB, there will be instants, and at some times they will be away and then in the negative direction. So, let us assume that, let us start counting time from this instant, that is, this is MF and this is MB, they are along the same space line, and then I am saying t is equal to 0 here, and each one of them is moving with a speed omega, forward and backward field. Therefore, at any arbitrary time, forward field will be here MF and backward field will be there MB, and this is your that initial point they were together. So, this will be omega t and this will be also omega t. Now, to find out the locus of the resultant field, what we will do is this, we will find out the x component of the resultant field. Mx will be nothing but Mf cos omega t, that is this projection, and plus Mb cos omega t. Similarly, this is the, suppose the x axis you arbitrarily tell, this is y axis, then My component will be Mf sin omega t minus Mb sin omega t. Is not therefore, if you eliminate that is therefore, that is the x coordinate and y coordinate. Therefore, I can say that cos omega t is equal to that x coordinate of m, resultant m, by Mf plus Mb, and sin omega t is Mx My by Mf minus Mb. So, eliminate time, square and add, therefore, I will get Mx square by Mf plus Mb whole square plus My by Mf minus Mb whole square. This must be equal to 1. Cos square omega t plus sin square omega t you do, and this is the equation of an ellipse. Okay. Therefore, the x coordinate of the resultant field is Mx, y coordinate of the resultant field is My at any time t. Therefore, if you eliminate time you get this. Therefore, it will be the locus of the resultant field, locus of the resultant field will be the will be an ellipse here, and it will be somewhat like this. This is the semi major axis Mf plus Mb and Mf minus Mb. So, that is essentially what I am telling, the resultant field will move with a speed omega, and it is like this. In case of 3-phase induction motor, the resultant field was lying on a circle of constant amplitude 3/2 some m max, is not. 3-phase induction motor, it was a circle. 3-phase induction motor. Strength of the field, rotating field was constant at all time. So, we see that there will be a resultant field, the locus of that will be lying on an ellipse, indicating that it is some rotating field, but not of equal strength. Okay. Achha, we will come to this a little later, but that is the idea that at any slip s, when it is moving, it is doing like that. Okay. Now, let us come to this. So, locus of the resultant field will be an ellipse in this case. Ellipse. Okay. So, please make habit to draw the torque slip characteristics correctly for 3-phase induction motor as well as for single phase induction motor. In single phase induction motor, the torque slip characteristics essentially will be like this. Not, it will start a little below from this, then this is S equal to 1, 0 torque, 0 to 1. 3-phase induction motor, it will be starting from here, it will go at S equal to 1, definite starting torque will be there, 3-phase. Achha, now the question remains that you cannot of course leave it at this stage without solving the problem of starting a 3-phase induction motor. You must do something so that the machine to the machine you incorporate some starting torque. Okay, this can be done by how to get starting torque. So, to do this, what you have to do is this is the rotor, cage rotor. Here you have to bring another winding, that main winding is the main thing. You have to bring now physically the other winding. It is nothing like a dream or thought, nothing is there but auxiliary winding. It is physically, the machine must be wind like a 2-phase induction motor with main winding having some turns N, this is also having some turns N, and these two will be the winding. And these two windings I will connect parallel and connect across a supply, so that both the windings will now carry current. And by doing something, I will incorporate this starting torque, and after the machine starts, then this auxiliary winding, this is called auxiliary winding, and this is the main winding. I will disconnect this auxiliary winding. What is done is this, there is a centrifugal switch, okay, and these two windings are connected in parallel, and then a supply. I am telling the last thing first, this is how it will look like. So, this winding is now physically present in the machine, There is no this way that way. Auxiliary winding is there with some what is called centrifugal switch, and this centrifugal switch is such that when the speed is very low or 0, this is closed. So, you switch on the supply here, there will be current in the auxiliary winding, there will be current in the main winding, and you will find machine is having some starting torque. It may have starting torque because now 2 windings in quadrature is present. Hopefully, there will be some sort of like 2-phase induction motor, perhaps it will develop a torque, that is why it is running like that. I will conclude at this stage, and it will pick up speed, and after it picks up speed, suppose speed becomes 70-80% of the nominal speed of the induction motor, then the centrifugal switch will automatically get open circuited, and since the machine has already attained speed, it will continue to run on a single winding. So, primarily if it is really a single phase induction motor, ultimately it has to run on a single winding, and auxiliary winding is brought in to assist the motor so that it can develop some starting torque. After it has developed starting torque, in presence of both main and auxiliary winding, machine will accelerate. After it reaches some speed, this switch, which is speed dependent, its operation is, it will open circuit. It is normally closed switch otherwise. So, that is the idea. Now, the question is, this auxiliary winding and main winding, what should I do? That is, these currents should be then manipulated, so that apparently it looks like I will try to make it operate as a 2-phase motor. See, if these 2 windings are identical and if you have balanced 2-phase supply available, which is however not the case. Suppose a 2-phase induction motor with a main and auxiliary winding is there, you connect it to one source, to a 2-phase source, such that the currents in both of them will be at 90° apart, then the problem would have been solved. But unfortunately, it is supply voltage is 3-phase or single phase. However, the simplicity of single phase induction motor is that we are going to make a simple motor like induction motor, which will run on single phase supply. That is the whole idea. Okay. So, what to do? Now, the thing is, then first we will see what is happening, how the starting torque depends on the main and auxiliary current. So, I will draw like this. This is my rotor, this is my rotor, and here is your main winding. Okay, it is connected to a single phase source. Suppose it is drawing a current of I bar m, and there is an auxiliary winding which is physically present now. Forget about the analysis where I assumed IA is 0, not like that. I will also connect it to this supply. Suppose that connection I am not showing, and this current is I bar A, and I will examine with both the coils present whether this thing can produce a starting torque. So, here I will assume n r equal to 0 straight, that is S equal to 1 forward field speed. So, what is the condition I have imposed? 2 coils are there, main and auxiliary, they are connected to single phase source, same source parallel, and at stationary condition mind you, this is no stationary condition, and in stationary condition I know forward slip and backward slip are same, is not 2 minus S. So, S equal to 1, this is I A. Acha, now obviously these two currents, let us not assume that these two coils are balanced or things like that, except that suppose number of turns are same. More general case we will be doing. What I am trying to tell, that this main winding current and auxiliary current, they may not be balanced. Okay. That is I m and I A, I m, that will be the most general case, I m and I A not balanced two phase current, not balanced two phase current. If that be the case, then I bar m can be written as its positive sequence M 1. This I have done earlier, but let me do it so that once again its negative sequence. Similarly, auxiliary current I bar A is equal to I bar A 1 plus I bar A 2, and this time this is not equal to 0. In our that imagined machine, I brought in auxiliary winding to understand what is going on actually, and I assumed I bar A is equal to 0, but here it is not like that, it is. But nonetheless, these two currents I m, I A are unbalanced two phase current. Therefore, they have their own positive and negative sequence of current, of which this I bar A then can be written as J I bar M 1 and minus J I bar M 2. I bar M 1 and I bar A 1 is a positive sequence, balanced system. This is negative sequence, balanced system. That is the thing. Okay. And I will not allow the rotor to rotate. I want to examine really starting torque can be available or not. So, it is a forward motor and once again a backward motor at S equal to 1 operating with the condition that I bar A not equal to 0, I bar M is also not equal to 0, and then this is the current. Now, the question is on the first place the equivalent circuit of the forward motor R 1 X 1 is not, and this is R 2 dashed by and this is X m by 2. In fact, that first one where for the forward motor there is V bar M 1, it is applied, is not forward motor. And there will be anyway, let us not complicate the issue. So, it is like this. Now, the question is these two currents, if it is connected across from the same supply like this, then at standstill condition, Auxiliary winding current will be that applied voltage V bar M by the impedance of the auxiliary winding what is seen by the supply Z bar A at standstill condition. Similarly, I bar M will be V bar M. No question of telling V bar M. Now, V is the supply. Okay. V by Z A, V by, because from the same supply I am giving the one. What is needed we will see later, but I am now telling you that these two currents I bar A and I bar M at S equal to 1 must have a phase angle difference between them. For example, what I am telling, this is suppose the supply voltage V bar, then this is the main winding current at S equal to 1, mind you, stationary condition, all things what I am talking now at stationary condition, I m and auxiliary current may be like this. So, this is the power factor angle of the auxiliary winding, this is the power factor angle of the main winding. That is what it means. Okay. Now, if that be the case and the angle between these two is some angle theta, therefore, there must be a phase difference between the main and auxiliary winding impedance, so that things will work, it will become clear after few steps. That is, if you see that this I bar M and I bar A, their power factor angles are same, then it will not give you any starting torque, that we will see. But the point is, okay, it offers an impedance Z A theta A and this impedance is Z M theta M, it is like this. Okay. That will be the case. Acha. Now, let us do a little bit of algebra. So, we have seen that I bar M, at least this much I can do in this lecture, I bar M1 plus I bar M2 and I bar A is equal to J I bar M1 minus J I bar M2. Okay. Let us try to express I M1 and I M2 in terms of I M and I A. So, what you do is this, you multiply this equation with J. So, it will be J I bar A is equal to minus I bar M1 and this will become plus J J minus 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 plus I bar M2. This will be the thing. So, from these two equations, if you add, you will get 2 add these two, you will get 2 I bar M2 from the right hand side. This will cancel out and you will get I bar M plus J I bar A. Similarly, if you subtract these two, you will get I bar M1 minus minus I bar M1. So, 2 I bar M1 is equal to I M minus J I bar A. So, these two are the main thing. Then what we will be doing is that torque will be proportional for the forward motor, that I m square into R2 dashed minus I m1 square into R2 dashed minus I m2 square into R2 dashed. Like that we will proceed. So, for today please go through this. We will continue with this next class starting. So, starting is very important.